Blake?
So can you look at number 25 on 3.10?
Yeah. Oops, insert. 25, you say?
Yes.
Okay, so this was the directions. And this was the problem. Okay. So this is relatively straightforward. The hardest part is, well, I'm going to do this as a linear approximation. I'm not going to do a differential. Given the choice, I'm probably always going to choose an linear approximation as opposed to a differential. They can do the same thing, but like linear approximation is just making a tangent line, which I'm already really good at. So like, why would I not do that? So the hardest part here is probably coming up with an equation to use. So the equation that I'm going to choose to use is I'm going to do a cube root of 1,000 plus x. So in this case, if I take the linear approximation of that equation and I evaluate it at 1, that'll be about the same thing as the cube root of 1,001. Everybody cool with that? Now the question becomes, why did I pick 1,000 plus x to put under the cube root? The cube root of 1,000 is a perfect cube, so it'll work out to a nice number. And so if I use x equals 0 as the other point on my tangent line, that is close to 1, the value for x that I want to evaluate. That's good. And it's spitting out a nice, neat, even number to build my tangent line with. I like that too. So that's why. All right. So to build my tangent line, I need a point. So the point I'm going to use is 0, 10. And then I need a slope. So the derivative of that, I'm going to think about it as 1,000 plus x to the 1/3. So it's 1/3 times the inside to the negative 2/3 times the derivative of the inside. Actually, we'll say m then is the derivative at 0. Let's see, 1,000 plus 0 is 1,000. Cube root of 1,000 is 10. 10 to the negative 2 is 1 over 100, so that becomes 1 over 300. So my linearization equation is going to be y minus y1 equals m times x minus x1. So there we go. And if I want 1, I'm just going to plug that in. And I think I get that when I type it into my calculator. So that's my approximation. Just to kind of illustrate you what we've done. So that's my approximation. Now I'll do it with an exponent. That's my actual cube root. Pretty good. Pretty good. Got like 4 or 5 places, decimal places of accuracy there. Pretty happy with that. Does that make sense for you, Blake?
Yeah.
Yeah, really the hardest part was getting, this to get going. Once you've fixed something there, everything after that, just like writing the tangent line and plugging 1 into it.
Maybe I'm forgetting something, but why did you make why did you make x 0 in the very first, at the very beginning?
So I need to do the tangent line at a point. So I need a point near an x value that's near 1, and I wanted something that was going to work out nicely.
Yeah,
So 0 was near 1, and also when I do f of 0, I get whole numbers. So like, yes, sir. That looks pretty good. Is that okay?
Yep, that makes sense.
So again, this stuff is just like, I need this to make my tangent line, right? I need the point and I need the slope. That's all I'm doing there, is just getting the ingredients for my tangent line. And then writing the tangent line is easy. And plugging 1 into it is easy. Really, the hardest part was coming up with the f of x. Or a good f of x anyways. Like... who else? There's probably a lot here. I know that these questions are not terribly difficult, but like if you don't understand what's going on, it's like, what do I do? Luke?
Could you take a look at number 7?
Sure. Grab all these. All right. So this has like 2 parts to it. It says first, verify the given a linear approximation at a equals 0. Okay. So if I look at 7, there's my linear approximation, and this is like my f of x. So I'm going to start by finding the linear approximation and seeing if it does indeed just become y equals x. And it says to use a equals 0, so I'm just going to do f of 0. So I plug that in, it's the natural log of 1, which is 0. And we'll do the derivative. So the derivative of the natural log of 1 plus x is 1 over the insides times the derivative of the inside. Okay, no big deal there. And then if I do f prime of 0, I get 1. So I have the point 0, 0, and the slope is 1. So I get y equals x. That looks good. Verified. Okay, not doing anything here other than just like checking. The next part then says determine the values of x for which the linear approximation is accurate within point 1. Okay, so I need, well, maybe let's start writing it this way. I need my linear approximation to be bigger than the actual value minus 0.1 and smaller than the actual value plus 0.1. And that'll make sure that it's always in between those two. Everybody's cool with that? So I'm just going to solve this set of inequalities here. I'm going to do it with the calculator because, quite frankly, when I see that natural log in there with an inequality, I don't love that. So let's see here. Minus. So I'm going to set a window here. I know the domain for the natural log here is going to be -1 to positive infinity. So -1 would be as small as I would need to go on the x. The window I chose was -0.5 to 1, and then -1 to 1 on the y's. That was just a little bit of guess and checking on my part.
How did you know the domain of that?
You can't take the natural log of non-positive numbers. So 0 and negative are bad. So -1 is the smallest number you could get. That makes a 0. Anything smaller than that's going to make a negative. So I know that all that stuff is garbo. Algebra 2. I know, right? It's like, oh no, that class again. So that's my this curving one is the linear or the logarithm, and then that's just y equals x. And I noticed that for all values of x, my linearization is bigger than the low end of my error range, right? So that's true for all real numbers. So that part's always going to be satisfied. Now let's look at the other end of it and see if there's any problems there. So I'll just go back in here and I'm just going to update that to be now plus 0.1. So again, this is my logarithm coming in here. And there's my linearization. So I'm interested in the part where the linearization is beneath the logarithm. Well, that happens starting here and then ending about there. Everybody agree with that? So second trace, do the intersect command, enter and enter to pick my two curves, scroll close to the 1 for the guess. So I have -383. And then the other intersection, second trace, intersect command, enter, enter, and then for the guess, we'll go close to this one, 0.516-ish. So that's the range of x's that my linearization will be within the desired error range. So what is this really saying? So if I take my actual function and I take my approximation and I do pick a value from this range, like, I don't know, say 0.1 or something. Bless you. If I do, oops, let's do this. Let's do the absolute value of, not a second. Y1, which is the actual, oops, I said 0.1, minus Y2, that's the approximation. The difference between those should be less than 0.1. Sure is, right? If I pick something outside of that range, like maybe we pick 0.6, the difference there will be bigger than 0.1, right? Or if I pick something smaller, you know, so like, just so I don't have to do anything crazy, I'm just going to do like -1, right? That's too small. Oh, I have a domain problem. Sure. Of course, Mr. Kulik, of course. All right, I'm going to do this the hard way. 0.9, negative 0.9. Ah! And again, error too big, right? That's all we're really saying there. Where did my things go now? There, that's just the page I was on. Does that make sense about what we actually found there and what we were doing? Blake?
So just to confirm on that, so that like 1.40 number, that is how much error we would have to give ourselves to have a linear approximation?
That's how much different the linear approximation is from the actual.
Oh, okay.
Okay, you're like 1.4 off the actual.
Okay.
That's all we're saying with that.
Okay.
That's the error.
Oh.
When x is when x is negative 0.9, that's the error basically.
Why did you put it in brackets?
Just so that the difference would always be positive, right? Because it's just saying like within this much. It doesn't matter if it's like negative 1.4 or positive 1.4. Both of those are equally bad, right? So I just put the absolute value around it just to like, now I don't have to worry about which one is on top of the other one. It's like that. Is that okay?
For 19, the wording kind of threw me off a bit of that.
This is probably the most involved one in the homework, to be honest with you, because it's asking you to give that picture also. Which is not trivial. All right, so it says compute delta y and dy for the given values of x and dx equal to delta x. Then sketch the figure showing line segments with lengths dx, dy, and delta y. All right, so first observation, if x, let's do this. Let's grab that figure 5 also. That'll help, right? So you guys can all see what it is that they're talking about. Did you go back and look at figure 5?
Yeah, I did.
Good. All right. So the first thing I'm going to do is figure out like these two values on the x-axis that I care about. Well, that's easy because I'm told x is equal to 2, and then I'm told then I need to figure out x plus delta x. That's no big deal because delta x we're told, right? Now I'm going to figure out my delta y, which is just going to be y, I'm sorry. In this case, let's use f of x plus delta x minus f of x. So that's like f of 1.6 minus f of 2. And when I plug that all in, I get 0.64. Right, what I'm just plugging those in here, right? That's my f of x. Okay. Now to get my dy, I know dy dx is just going to be 2 minus 2x. And if I multiply both sides by dx, I have that. And if I evaluate this, then where x is equal to 2 and dx is equal to delta x, I get 2 minus 2 times 2 times negative 0.4. And when I do that, I get 0.8. Okay with that? All right, now let's draw this picture over here. I'm going to try to give myself a little bit of space so that I have room to label some things. So I'm going to start first by graphing y equals 2x minus x squared. So if I set the y equal to 0, I can see that I can solve this to get the x-intercepts. Those will be helpful in graphing. So I have the 0.00, and then I'm going to go by, and then the 0.20. Actually, I'm not going to bother labeling that. I'm just going to call this x equals 2. And then I want the vertex for that parabola. How do I find the vertex of a parabola? Negative b over 2a. Yep. So negative 2 over 2 times negative 1, which is just 1. And then to find the y-coordinate, I just plug that back in. So that's 1. So there's my, there's my f of x. Now I'm going to need to graph the tangent line here, right? That's the purple. So I'm going to need to create that. So if I take the derivative evaluated at 2, that's negative 2. And if I take f of 2, that was 0. So that's going to be the stuff I need to write my equation for my tangent line. Is okay with that? Check.
Why was negative 2 confused?
Well, that's just the derivative, right?
Oh,
when I plugged in 2.
Oh, okay, yeah.
I just did it. I mean, I have it right there. I'm just going to like pull that number because that's all that is, right?
Yeah.
You could plug it in fresh again if you wanted to. That's fine. So I have 2, 0. And then if I plug 1 in for x, I get 2. So this is my tangent line. Everybody's okay there? So there's x equals 1 or 2. And then I guess like x equal or x plus delta x, which is 1.6, be there. Right? A little bit more than halfway. So this piece right here is my delta x. Everybody's okay with that? So if I take this point here down, that is the change in y, right? At x, the y coordinate was 0. So this is just like delta y. Everybody's cool with that? And if I take this point here I look at this, that's dy. So that's the difference between f of x and my linearization, right? So kind of in general, that's kind of what we're saying as far as labeling the parts for our picture. Now, if you look at figure 5, it was a little bit different because the linearization in figure 5 was an underestimate of the function. Here in our case, our linearization is an overestimate. So that's why the picture is going to look a little bit different. But that'll do it for us there, Luke. Does that feel okay? Blake?
This is like a question, so I was wondering if you could do number 37.
Which one?
Number 37.
37. So 37 says use differentials to find a formula for the approximation or approximate volume of a thin cylindrical shell with height h, inner radius r, and thickness delta r. So let's just kind of start with a picture. So I'm going to just take a cross section of that cylinder. And it says a cylindrical shell. So what it means is like a tube, right? Like a pipe. And it says that we have an inner radius of r and a thickness of delta r. And then the height of that cylinder is h. So just like whatever. Or actually, it's probably easy. It'll look better if I draw it this way, right? If I do this. Draw it that way. That looks a little better, right? The perspective's a little better. All right. So the volume for a cylinder is pi r squared h. So the delta V should be approximately the same thing as dV. That's all we're doing with our linear approximations. So dV dr is going to be pi times 2r times h. And if we multiply both sides by dr, I have 2 pi r h dr, or really 2 pi r h delta r. Since we're making this approximation, we can just say that dr is the same as delta r.
So unlike unlike the related grades, in this unit when we're taking the derivative of things, and that delta, it's not representing a change in anything.
So that delta R is like the difference between like I'll explain in a moment kind of what we're doing here. So what we're doing is like that thickness of the tube eventually becomes negligible if we just use the inner radius. We can approximate the volume, like without the thickness is basically all we're doing there. So the thinner that gets as dr approaches 0, our approximation ends up getting closer and closer to the actual. That's all we're really saying.
How are we able to get from dr to delta r?
Because we're saying that delta v is approximately dv.
Okay.
Right. If that's the case, then delta r is approximately dr.
Okay.
Right. That's still using a linear. That's what differentials are. It's just a linear approximation that we can say that, okay, like the change in r is the same as the differential, like that's all we're kind of saying. Okay. So that's like part A, right? Find a formula for the approximate volume and then part B says, what is the error involved in using the formula from part A? Well, our error is going to be the absolute value in the actual change in volume minus our approximate change in volume. Oops. Everybody's okay with that? Okay. And now I can see pretty quickly from the context of this problem if I'm calculating the volume, the actual volume versus this approximation where we're just using the inner radius and the thickness, that's going to be an underestimate. So I'm going to just drop the absolute value here because I know that it's going to be a positive value here. So the dr or the dv we know, that's just what we did in the previous part. Now, the volume here for my pipe is going to be the volume of the outer minus the volume of the inner. So the volume of the outer is going to be pi r squared. Oops. But the radius in this case is going to be r plus delta r, right? That's the outer shell. And then the inner shell is just going to be pi r squared h. Hello.
I just need tea.
Sure, no problem. Everybody's okay? I'm going to FOIL here, and at the same time, I'm going to distribute the pi and h through. Let's put some parentheses around that delta R. So I notice here that I have a plus one of these and a minus one of those. So those can cancel out. And then I have a plus one of these and a minus one of these. So those can cancel out. So what are we left with here? Is this. Absolutely. Notice here that as delta R goes to 0, what does this error become? Zero, right? Which is what you'd expect, that as your pipe gets less and less thickness, my approximation where I kind of don't worry so much about how thick the thing is becomes better and better and better, right? As that delta R decreases, this number is going to get better. My error is going to get closer to 0, which is what I'd hope, right? The thinner that pipe, the better the approximation I have is. So just symboly and really understanding what it is that you're doing, which is the tough part. But when it talks about a differential, all you're doing is taking the derivative and multiplying the denominator to both sides. That's all you're talking about doing to find a differential. So if I just take the volume of something that, with just respect to the inner radius, and I find that differential, that's going to approximate as if that thickness was 0, which is fine. So what I'm doing here, I'm using this as my volume, which is just the volume of the insides. Now, if I look at the derivative of that, that's the rate that's changing with respect to R, the rate that volume is changing as R changes. If I multiply the change in R over, I have the rate that volume is changing. And if I fix that change in R, what I have is a volume for something that's kind of like hollow. Right? Because you have the change in R built into it.
Yeah.
That's like the subtraction in the other part. Is that something? Sure. More 310 stuff, or do you want to talk about review problem stuff? It's up to you guys. I'm okay. You guys pick good ones. These are pretty much like some of every type. I think you picked something. So you should have good models to finish up whatever else you might need. Should we look at the review then? Or the study guide, I guess I called it this time. As just a heads up, the fifth hour caught a couple of caught one typo, or arithmetic error, I guess I should say, in the answer key. So I went and updated the answer key there. Where was it? Oops, not this. Yeah, here it was. When I added my fractions, I added the fraction wrong on 4B. So I updated the key. And then I just did a typo on 5B. So again, I updated the key there. I started off doing the right thing. I said, plugging 3 in, then I plugged 4 in. I don't know why I did that. Actually, I do know why I did it, because I wrote the question I ended up not writing what I intended, but it's fine. Like, it was still whatever. Did you want to go through any of these or talk about the format or anything here? It's your guys' time, man. I'm happy to do whatever you guys want to do.
So are we not doing another lesson today?
Or not.
Okay. With that, do you mind just going over really quick and reviewing the intermediate value here?
Mm-hmm. Sure. So the intermediate value theorem says if f of x is continuous on some, I can't remember if it has to be open, I think it has to be closed interval AB. Then let's see. Okay, yeah. Then for C in that interval, if okay, let me just screen grab it. I forget how this exactly goes. I can use it. Probably here in 2.5. Yep. Come on now. You wouldn't let me do that? Everything is highlighted and unhighlight this thing. All right, fine. Be a duty head. There, fine. All right, what do we got here? It says that suppose that f is continuous on the closed interval a, b, I had that part, and n be some number between f of a and f of b, where those are not the same value, or where f of a and f of b are not the same. Then there exists a c on the open interval a, b such that f of c is equal to n. So what this is saying is, like, we have some function that's continuous from a to b. You can pick anything here in between f of a and f of b. So let's say that we're going to pick this value to be c. Means that at least somewhere on that function, we call that n, there's some x value that's going to have that y coordinate. Okay, so for example, say I want to show that polynomial, actually I think it's probably proper if I write it that way, has at least one real root. So what I want to do is show that for f of x equals this, there exists some c in the real numbers such that f of c is equal to 0. So this 0 is like my n in the statement. So what I want to do is I first have to show that this is continuous. How do I do that? Perfect. Yep. And you'd say continuous on its domain, which is, yeah. So we're continuous everywhere. Fantastic. Now what I would need to do is I need to show that this thing takes on a negative value somewhere and a positive value somewhere. Well, f of 0, I can tell gives me a negative value. And f of 1 gives me a positive value. So I can say since f of 0 is less than 0 is less than f of 1, there exists a C on the interval 0, 1, such that f of C is equal to 0. I guess I should say the IVT states there exists a C on 0, 1, such that f of C is equal to 0. So all you're doing is showing the existence of some x that gives you a specific y. Right? It doesn't tell you what the x is. Can't help you do that, but it can show you that there has to be one. Right? Now, could there be more than one c that gives you that x value? Sure, but is the question asked for just at least one? We've shown there's one, that's good enough. If we wanted exactly one, that would be harder. We couldn't use just the IVT to get that. You'd need to use something else. And in fact, we'll do that problem in 4.1 or 4.2. I can't remember which one, but we do it. Is that okay, Luke? So if you want to show, again, if you want to show that a function takes on a specific value for y, or want to show that a certain value for x can give you a certain value for y, the IVT is the tool that you'd use. And all you need to do is you got to show continuity and then find two y values that sandwich the desired y value, and you know you have what you need. Is that okay?
So you want to use this if you want to find a specific x.
So what you can use it for is you can show that either a function takes on a specific y coordinate or takes a specific value, or you can use it to show that a function, there's an x coordinate for that function that gives some specific y value. So in this problem that we were just doing, we wanted to show that there was some x that gives you this specific y value, right? If I just wanted to show that, I could have alternatively reworded this problem to just ask, like, show that f of x is equal to 0 somewhere, right? Or there is an x such that f of x is equal to 0, right? It's really, it's doing the same thing, it's just like different verbiage or whatever. Does that feel better? Okay. Jack?
This is kind of a little bit, let's just look at a review.
Sure.
So for 3.7, number 7, would you mind doing C through D?
3.7, number 7.
So I got A and B, but C through D, set the final answer. Right? So I just
Oh, okay. Probably not. It's probably just got confused at what to be using when is usually the problem on something like that. You said C?
yeah.
Okay. So for C, what I'm going to be doing is I'm going to take h prime of t. I'm going to set that equal to 0. Because I know that, like, if I'm looking at a height function, at the maximum height, we're going to have a place where the slope is 0.
Yeah.
So I'm just going to be solving that. Oh, we already did that in part B. Sorry. And let's say that answer is just like T max or something. For part C, then, I'm going to take my height function and just plug T max into it. That'll give me the actual height, the maximum height. Right? Sorry. Read the question all the way. D asks, when does this hit the ground? So that's going to be where the height is 0. Right? So we started at some elevated position and then like hits the ground some later point. You'll get 2 answers for it, but one will be negative time, which makes no sense. And then for part E, it asks, what is the velocity when it hits the ground? So let's say that T is called T ground. I'm just going to take that answer and plug it into the derivative.
Okay, yeah, that's where I messed up. I put that. Thank you.
You're welcome. So this question is just like, the calculus part is easy. It's just like jumping back and forth, like which one do I want, the derivative or the regular? Yeah. Yep. So again, it's just like being careful and being like, okay, height 0, height, that's the original. If I want velocity 0, that's the derivative, right?
Yeah.
So it's just like making sure you're really reading there carefully and going, oh, if it's asking about heights, I need to use the original. Unless it's like one of those like extreme value pieces where it's like, when is it at the maximum or minimum? Right? Okay. And I didn't really solve anything here, Jack, but I think I did like enough.
Yeah, no,
like the algebra is pretty easy.
Yeah, I just plugged it.
Okay. Yeah. It's, again, most of these questions, like the setup is the trick. What else you guys got?
So on the review, so when it says so there's 3.10 problems. It says these will be multi-part story problems that will also draw on some previous skills such as implicit differentiation and the IVT. What are those going to look like?
So that's why I gave you 2 examples afterwards. So like number 4 is one where you're going to use the implicit differentiation, right? And then like for number 5, I could say like, show that the function h of t takes on value of, 55 at some time, right? How could you prove that?
Okay.
Again, you got to show continuity first. How do I know that h is continuous? Because it's not defined as an equation here. It's given to you in the table.
You say it's continuous to 0 through 10.
But why? That's what you need to show, yes.
Well, it says given by the twice differentiable function h.
Great.
And in order to take the derivative of something, it must be continuous.
Very good. There you go. So the differentiability implies continuity.
Okay.
So there's your continuity. And then you can simply say that since h of 4 or h of 7 is less than 55 and h of 4 is greater than 55, then we know there's a c somewhere between 4 and 7 such that f of c is equal to 55 by the IVT. Done.
So no math.
No math.
Only the concept.
Yep.
Okay.
Yep. So that would be a way that I'd use like the IVT on a problem like this where there's a table. It's just to show that some value in between exists. And that's
For something like applicable like this, where it's actually dealing with like, voltage, there would always, or theoretically, there would always have to be a value in order to get 55, because it's just not going to make that jump from, or that, I guess, that decrease from 67 to 51 instantaneously.
Yeah, and again, probably where they'd hide that is in the paragraph, like I did with the twice differentiable. Now, be careful who you're saying that to, because if you're talking to like a quantum physics expert, they'd be like, "Well, sure it does," because we know energy is quantized, right? Like energy changes in discrete packages called the quanta. It's just that amount of energy change is so small that it's like, from our perspective, it might as well be continuous.
Yeah.
But it's not actually continuous. But it's close enough that it doesn't matter to us, like doing this kind of thing. Does that make sense? I don't know. You took AP Chem, right?
No.
No.
I'm not.
Okay. Oh, okay. I think you probably still talk about that in honors chem.
It's software here.
Okay, fair enough. Yeah, that's fair. That's fair. I think that's Max Planck is the energy is quantized. I think Planck's constant is the amount. That's the amount of energy in one quanta, which is cool, right? You don't expect that. Like things at the micro at subatomic scale are very, very weird. Nothing works the way you'd anticipate it. Either that or we have everything wrong. Like all our models are wrong. Even though it's probably the most supported set of hypotheses, scientific hypotheses, in the history of human civilization. Because like all of our electronics and everything are built around these ideas. And they never stop working. At least for physics reasons. For engineering reasons, they stop working. This is just me babbling now. How are you guys feeling otherwise? It's all right. We'll do this real quick then, since seems like we've had a little bit of a lull. For the asynchronous days, I made a video for 4.1 and 4.2, and these are the 4.1 and 4.2 problems. Now, completely within your prerogative to just put that on the back burner till after you take the test and deal with that, like that's a Tuesday, Wednesday problem. Totally understandable, like I probably would do something similar in your shoes. Keep in mind though, when we meet again on, would be Thursday, next week, we'll be starting, after the test on Thursday, we'll be starting on 4.3. So try to make sure you've at least watched the videos or the lessons and tried to do a little bit. 4.2, I think, was like 40-ish minutes. And then 4.1 was like 40-ish, and 4.2 was only like 20. So if you break those up and don't do them back to back, that's not so bad. Cool with that. Both the ideas are pretty straightforward. 4.1 is all about like maxes and mins, finding maxes and minimums for functions using calculus. And then 4.2 is all about the mean value theorem, which is just like kind of like a more specific version of the intermediate value theorem, where it just basically says that, okay, somewhere in between, if you have a function that's continuous over some closed interval, somewhere in between, or somewhere on that interval, the function takes on the value that's the average of the starting point and end point. That's all it's saying. Teagues.
Two questions.
Sure.
So on the tests, there's not going to be much 3.8, or there's not going to be any 3.8 because it's like that's an introduction to 3.9.
Yes. Yeah, 3.8 was, well, there wasn't much calculus in it.
Yeah.
The calculus was, if you have something, a differential equation of this form, you can use this equation to model or to solve it. That was all the calculus, and everything after that was just like algebra. So just kind of, in my experience looking for AP things, I didn't see anywhere where that really came up. So I just omitted it.
And then for the 3.10 problems, I guess this is pretty self-explanatory, but if we know how to do those ones, we should be pretty good.
Yeah.
Because that's what I would.
Yeah. For the most part, like 310 boils down to, if we ask for an approximation, just using it, writing a tangent line and plugging the number into the tangent line to get your approximation. That's what it boils down to. Everything in 310 boils down to basically boils down to writing a tangent line and then using that to make some approximation. And that's the kind of thing that I've seen over and over and over on the AP. Like that's the kind of linear approximation that they're talking about. Like I haven't heard differential in me looking over questions. I have not seen that term even pop up. So again, my emphasis is on the linear approximation piece or the tangent line approximation piece, since that appears to be a typical AP question. Yeah, no problem. Happy to be specific, right? Like, helps you guys. I want you to do well. I don't want you to waste a bunch of time studying stuff that I don't care that you know or not. Or to have mastery over anyways. Like, you kind of know it. That's enough. Amanda? Certainly. Oh, excuse me. You guys feel okay on your related rate stuff? Doing the problems probably helped. Where it's like, here's some problems, here's the answers, like, figure her out. And again, that's something that felt very hard in the beginning, but probably as you got more experience with it, seemed to get easier and easier and easier, which is good, right? Just takes some time. All right, I'm going to stop the recording because it feels like we've kind of run out of stuff.